Welcome to this introductory video on the Standard Model of particle physics. Today, we're going to explore the complete Standard Model Lagrangian, the mathematical framework that describes all known fundamental particles and three of the four fundamental forces in our universe. The Standard Model is our most successful theory of particle physics, describing the elementary particles and their interactions through the strong, weak, and electromagnetic forces. It includes quarks and leptons as the building blocks of matter and describes force carrier particles like the photon, gluons W and Z bosons, along with the Higgs boson, which gives mass to other particles. All of these particles and their interactions are elegantly described by a single mathematical expression called the Standard Model Lagrangian. The Lagrangian is named after Joseph Louis Lagrange, and it provides a compact way to encode all the physics of the Standard Model. From this mathematical formula, we can calculate everything about particle interactions, from scattering probabilities to decay rates. Now, let's look at the full Standard Model Lagrangian. It appears complex, but we'll break it down step by step. This is the complete Lagrangian of the Standard Model, written in a schematic form. It consists of 6 main parts that we'll explore one by one. Let's start with the first term. This is the QCD gauge term, describing the kinetic energy and self-interactions of gluons. G superscript, a subscript, mu represents the gluon field strength tensor. It's defined as the partial derivative of the gluon field minus the partial derivative in the other direction, plus a term describing how gluons interact with themselves. This self-interaction term is unique to non-abelian gauge theories like QCD and is responsible for properties like color confinement, the fact that we never observe free quarks. Moving to the second term of our Lagrangian, this describes the electroweak gauge sector, which includes the W and B fields. The W fields correspond to the SU2 weak isospin gauge group, while the B field corresponds to the U1 hypercharge gauge group. Like the gluon field, the W field strength tensor includes self-interaction terms, but the B field doesn't have these as U1 is an abelian group. After electroweak symmetry breaking, these fields mix to give us the physical W plus, W minus, Z naught bosons, and the photon. The third term in our Lagrangian is the Fermion kinetic term. It describes the free propagation of fermions and their interactions with the gauge bosons. The sum is over all fermion fields, quarks and leptons, both left and right-handed. The key element here is the covariant derivative, which ensures gauge invariance and introduces interactions with the gauge fields. When expanded, the covariant derivative includes terms for each of the 3 gauge interactions: strong, weak, and hypercharge. The fourth term is the Higgs kinetic term. It describes the propagation of the Higgs field and its interactions with gauge bosons. The Higgs field phi is a complex scalar SU2 doublet with hypercharge 1/2. Like with fermions, we use a covariant derivative to ensure gauge invariance, but since the Higgs is a scalar, there's no Dirac matrix gamma mu involved. This term is crucial for the mass generation of the W and Z bosons through the Higgs mechanism. The fifth term in our Lagrangian is the Higgs potential. This is what drives spontaneous symmetry breaking. The potential has the form of a quadratic term plus a quartic term. When mu squared is negative and lambda is positive, the potential takes a famous Mexican hat shape where the minimum energy state is not at 0, but at a circle of non-zero field values. The Higgs field spontaneously chooses a particular direction in this circle, breaking the SU2 times U1 symmetry down to U1 electromagnetic.